Hello, welcome back. In this segment, I wanted to talk about the Euclid's theorem. The number of primes is infinite, which is a remarkable result because we would like to know there are infinite number of primes. Euclid thought about it and gave a proof. It's quite a fascinating proof, actually. This problem seems to me, at least, that it's very complicated, right? How do you show something is infinite? The number of primes is infinite. Okay, this is good news for cryptography because the infinite number of primes we can leverage for cryptographic algorithms and protocols. Okay. So let's think about the proof. So the proof that I'm going to talk about is arguably given by Euclid, 200, 300 BC time frame. It's quite a fascinating idea. So the proof is based on contradiction again. Suppose we assume the number of primes is finite. Okay, so let's assume there are only these are the only set of primes we have. Well, what can we do now? Let's define a new number as follows. Let's say capital N is a new number, which is nothing but product of all these primes that I have shown earlier, P1 into P2, and add 1 to it. Okay. So what can we say about this number N, which we newly formed? Okay. Clearly, N is greater than all the prime numbers P1 to Pm because we multiplied all the prime numbers. Therefore, the answer must be greater than each of these numbers, right? That's the product of positive numbers. Each prime number pi is, of course, greater than or equal to 2, right? Therefore, if you multiply all the positive numbers, the result will be greater than all of the numbers. That's basically what I'm trying to say here. So n must be greater than all of the prime numbers. Okay. Now the question is, can we write n as a product of these numbers? Okay. In the previous segment, I proved that every number can be represented as product of primes. Of course, assuming n itself is not a prime. So we need to now talk about that scenario. Okay. And I'm going to argue now that n cannot be represented as product of the primes that we have here. We assumed only the finite set of primes. Remember, this is the only finite set. So I'm going to prove now a couple of things. First, take some number pi. Okay, pi can be p1, p2, pm, anything. Suppose you take any number pi. I argue that any pi, okay, will not divide n. Okay, think about it. Why? Suppose pi divides n, then pi will also divide n minus P1 times P2 all the way until Pm. Okay, why is this? Let's think through this. So what is the meaning of me saying that if Pi divides n, that means n can be represented as Pi times something, right? Pi times some constant. Okay, which means now let's focus here. Which means n can be represented as Pi times some constant, and Pi is already somewhere here. So we can take Pi common. That means we can show Pi divides n minus P1 through Pm product. Okay. But what is the value of n minus P1 times P2 all the way Pm, which is nothing but 1, because we just move this whole thing to the left, basically, or subtract both sides by P1 to Pm, which means the prime number Pi divides 1, which is impossible because prime numbers are greater than or equal to 2. So it cannot divide a number 1, okay, which is a contradiction. Okay, this is a contradiction. So Pi cannot divide n, okay, and Pi is an arbitrary Pi. So none of the prime numbers P1 through Pm will divide n. Okay, that means n cannot be represented as product of the primes, which is a problem also because in the previous segment we proved that every number n must be represented as product of primes. Okay, if you have only a finite number of primes, you will get a contradiction like the one that I have shown to you. So the number of primes must be infinite. That is his argument. Beautiful proof. Okay, thank you.